My name is Peter Tankov. I'm professor of quantitative finance at NSIO, the National School of Statistics and Economic Administration, and scientific director of the Park Foundation at Louis Bachelier Institute. Today, I will speak to you about quantitative methods in sustainable finance. Quantitative finance is a collection of mathematical tools and methods based on advanced probability and statistics and used for solving a range of problems in the financial industry, such as pricing derivative products through dynamic hedging, systematic portfolio construction, quantitative risk management, and more recently, algorithmic trading. Key milestones in the development of quantitative finance are the Markowitz portfolio theory, 1952, which led to the development of modern portfolio optimization techniques based on a trade-off between risk and return, Black-Scholes option pricing formula, 1973, which transformed derivatives industry, and the value at risk, developed at JP Morgan in 1994, and which is the cornerstone of the modern approach to financial risk management. Sustainable finance involves taking environmental, social, and governance considerations into account when making investment decisions, both from the point of view of maximizing positive impacts of investments on the environment and the society, and minimizing negative ones, and from the point of view of accounting for various sources of risk related to them. It relies on a range of new data sources to quantify these characteristics. Nevertheless, sustainable investors also care about the financial performance of their assets. Thus, risk and return analysis techniques are still relevant for them. Without pretending to cover all quantitative techniques used in sustainable finance, our aim today is to compare the modern approaches used in the two domains, emphasizing the areas and applications where sustainable finance has something to learn from its quantitative cousin. Models in quantitative finance are probabilistic representations of possible future evolutions of financial markets. They are used to price assets and financial products, quantify the risk of financial positions, design trading strategies, and determine provisions for unhedged risks. Although based on specific assumptions and simplifications of real-world phenomena, they allow to structure decision-making and mitigate financial risks if used wisely. Quantitative models work best for short to medium-term horizons, not too long so that stationarity can be assumed and forecasts remain reliable, and not too short so that market microstructure effects and other imperfections related to, say, discrete time do not come into play. A typical risk management framework for, say, an exotic option trading desk would consist of a pricing model used to determine price quotes for options, strategies for hedging the risk, which are well represented within the model, and provisions for the risks which are not well represented. In other words, the model may and will be too simple compared to the reality. But if the trio model, hedging strategies, provisions is sufficiently conservative, it can still be successfully used to manage the trading desk's risks. Many of the above problems also arise in sustainable finance. Although exotic structured products are less common, relevant problems include pricing financial assets, stocks taking into account various ESG-related premia and market frictions, pricing and hedging bonds exposed to climate and other nature-related risks, finding a trade-off between financial and ESG performance in portfolio construction, building net zero and Paris-aligned portfolios. These problems also require models to be solved rigorously. The modeling is, however, made complex by the long-term nature of the risks involved and the often poor quality of data sources. The long-term nature of climate and nature-related financial risks makes it difficult to use so-called reduced-form models, which are common in quantitative finance. In reduced-form models, prices of fundamental assets, such as stocks, are modeled directly by exogenous stochastic processes, whose parameters are calibrated to data. By contrast, in structural models, prices are deduced from market fundamentals, and in equilibrium models, prices are obtained as a result of interaction of market participants. Structural and equilibrium models are better suited for modeling long-term risks because of their capacity to adapt to changing market conditions. However, they require much more computational power to run, as, for example, in equilibrium models, the decisions of individual agents must be described and taken into account. Another reason of model complexity in sustainable finance comes from the necessity to model risk factors other than prices, such as climate and macroeconomic variables, which means that model dimension, number of variables, is much larger than in quantitative finance. Since these models describe different aspects of the future, such as climate, economy, finance, etc., they are known as integrated assessment models, IAM. As a result of this complexity, most IAMs are deterministic. That is, they do not include random noises and produce just a few simulations, as we can see in the figure, which shows in the left-hand side the carbon emissions and in the right-hand side the carbon price in the 6 scenarios of the NGFS scenario database release 3. On the other hand, option prices in quantitative finance are typically computed using tens of thousands of simulations, which explore the randomness of possible futures through branching scenarios, as shown in this figure. This complexity makes it difficult to analyze the robustness of models and quantify the impact of parameter uncertainty on the final results. Research on uncertainty quantification of climate economy integrated assessment models is only now starting to appear. For example, in a recent paper by Kai and Lonsek, a variant of a rather classical IAM with stochastic risks was solved in 8 hours on a blue water supercomputer with 110,000 cores running in parallel. During the last 20 years, quantitative finance has developed efficient algorithms for solving large dimensional stochastic optimization problems with much less computing power, using cleverly generated trajectories or neural networks. Maybe climate economics has something to learn here. One important domain where sustainable finance has a lot to learn from quantitative finance is related to model governance and model validation. Models have been used in quantitative finance for at least 50 years, and sound principles have been established regarding the proper use of models and the management of model risk. For example, the famous SR 1107 guideline of the Federal Reserve, published in 2011, defines the model as a combination of 3 components. Information input component, which delivers assumptions and data to the model. Processing component, which transforms inputs into estimates. Reporting component, which translates the estimates into useful business information. In this framework, model risk is defined as the risk of either having a model which contains fundamental errors and may produce inaccurate outputs, or having a correct model which is used incorrectly or inappropriately. According to the guideline, model risk should be managed through robust model development, implementation and use, sound model validation process, and finally, a governance system which sets an effective framework with defined roles and responsibilities for clear communication of model limitations and assumptions, as well as the authority to restrict model usage. Tools for mitigating model risk include establishing limits on model use, monitoring model performance, adjusting or revising models over time, and supplementing model results with other analysis and information. A key component of model governance in quantitative finance is a model validation framework, which includes the following steps: evaluation of conceptual soundness, including developmental evidence, assessing the quality of model design and construction, ongoing monitoring, including process verification and benchmarking, which must confirm that the model is appropriately implemented and is being used and is performing as intended. Outcomes analysis, including backtesting, comparison of model outputs to corresponding actual outcomes. Documentation of model development and validation, which should be sufficiently detailed so that parties unfamiliar with the model can understand how the model operates, its limitations, and its key assumptions. These basic principles are further developed in the Fundamental Review of Trading Book, Guidance of the Basel Committee, 2016. In sustainable finance, sound model governance and validation principles are yet to be established. At present, financial actors meet their needs using off-the-shelf scenarios. This seems to be the simplest choice, but these scenarios are mostly based on black box integrated assessment models, whose details are often not fully public, and whose validation, in consequence, is problematic. An alternative is to develop an in-house modeling capacity, which would allow the financial actors to control the entire modeling chain and implement appropriate governance and validation procedures. This, however, in addition to the skills in financial and quantitative modeling, requires knowledge in macroeconomics, energy economics, and environmental sciences, which most financial institutions do not have at present. This can also lead to multiplication of models leading to different conclusions, which is particularly dangerous in the highly politicized domain of climate finance. The answer is to intensify the dialogue between the financial institutions and various modeling communities, to promote an interdisciplinary and open approach in model development, along the lines of the guiding principles of model design and governance established by the regulator for quantitative finance models. The modern approach to risk assessment and banking supervision is arguably the most significant application of quantitative methods to finance. The principles of banking supervision were developed in the successive Basel Accords, from the first one in 1988, dealing with the banking book only, to the third one published in 2011 in the aftermath of the financial crisis, as well as additional regulations such as the Market Risk Amendment of 1996, which introduced the value at risk, and the Fundamental Review of Trading Book of 2016. Within the Basel framework, regulators monitor various regulatory ratios, the most important of which is the capital ratio. Quantitative methods are used to calculate the capital, the value of certain illiquid assets, as well as for the calculation of the value of risk-weighted assets. Risk measures such as value at risk, stressed value at risk, or the expected shortfall are used at this point. Everyday risk and capital adequacy assessments are thus based on probabilistic models of market evolution. To complement this probabilistic perspective, supervisory prudential stress tests are conducted regularly to evaluate the bank's resilience to scenarios, which may not be well represented by the probabilistic models, but are nevertheless relevant and sufficiently severe to warrant special attention. These stress tests are conducted by supervisors according to a specific schedule. For example, the ECB conducts them on a biannual basis. But banks are expected to implement internal stress tests with a higher frequency. Modern financial risk assessment is thus a combination of probabilistic approaches and stress testing to account for specific non-probabilistic scenarios. In the recent years, and especially since the climate-related financial risks came into the limelight with Mark Kearney's speech Tragedy of the Horizons in 2015, supervisors started to develop frameworks for climate risk assessment. And the first climate stress tests were conducted by central banks starting from 2020. These stress tests are similar to prudential stress tests in some aspects, but very different from them otherwise. Most importantly, while prudential stress tests use either historical scenarios corresponding to a crisis period or hypothetical scenarios where a specific risk factor is stressed, climate stress tests are typically based on prospective scenarios produced by integrated assessment models under specific climate and policy assumptions. While the stress testing component of the financial risk management framework has been replicated for climate stress tests, this is not the case for the probabilistic component, based on risk measures. This is to some extent justified by the long-term nature of climate risks and by the difficulty to assign a probability to prospective scenarios. However, since climate stress testing is not a complementary tool aiming to quantify the impact of plausible but rare severe scenarios, but the main method for assessing climate risks, which aims to explore different likely outcomes, it is clearly not sufficient to use a small number of deterministic scenarios. Climate risk associated to, say, a disorderly transition scenario strongly depends on the nature of this scenario, and a single scenario may miss important mechanisms of risk materialization. Since we are dealing with likely events whose nature is not perfectly known, it is important to explore a multitude of possible futures, and for this a probabilistic approach is necessary. One possible way forward is given by the recent approaches in the literature, inspired by quantitative finance, which introduce probabilistic components into IAM and allow to quantify the uncertainty and generate a multitude of scenarios. A second drawback of present-day climate stress testing approaches is their inability to describe endogenous financial system dynamics, such as herd behavior, fire sales, credit contagion, which can exacerbate financial crises triggered by external factors such as climate. The mechanisms behind these phenomena are starting to be relatively well understood in quantitative finance literature, but climate stress tests are usually based on very simple models for the propagation of climate risks to the financial sector, which work at the level of a single asset and do not account for nonlinear interactions. A key objective of sustainable finance is to redirect financial flows away from activities with high negative impacts and towards activities compatible with sustainable development. One way to achieve this is to incorporate green net zero considerations into portfolio choice. As similar shares of funds are managed with passive and active investment strategies, it is necessary to both develop green indices for passive investment and green active investment strategies. Key points here are: 1. Determine which investments are considered green or net zero and measure their greenness. 2. Understand the investor's preference for greenness and construct indices or strategies taking this preference into account. The definition of green asset is provided, for example, by the European taxonomy. However, assets which are not green, but which are on the right track for net zero in 2050, or which are necessary for the transition, should also be funded. The notion of net zero alignment is more difficult to define, as it involves not only the present activities of the company, but also the future trajectory and transition plan. Quantitative approaches are needed to measure the performance of the company beyond what the company itself wishes to report. For example, carbon emissions are reported on an annual basis, and the emissions for year N are usually published well into the year N+1. Quantitative methods such as machine learning or satellite data analysis may be used to predict emissions, 1, before they are available and in high frequency, 2, for companies which do not publish emission data. Quantitative methods, forecasting methodologies, may also be used to predict the future evolution of the company based on its past performance and the available data, to measure whether it is on track for net zero. The second step, portfolio construction, is also based on quantitative approaches. One of the first results in quantitative finance is the Markowitz efficient frontier. If the investors want to maximize portfolio return and minimize its risk, then all efficient portfolios will draw a curve in the risk-return space, called the efficient frontier. Modern portfolio choice often uses stochastic control approaches, which originated with the celebrated Merton portfolio problem. When green, ESG, net zero considerations come into play, the efficient frontier theory breaks down, since the investors want at the same time to 1. Maximize the portfolio's expected return, 2. Maximize its environmental performance, and 3. Minimize its risk. It is therefore essential to define an optimization criterion taking into account investor preferences in an appropriate way. One approach is to look for the portfolio with the highest Sharpe ratio under a given ESG score constraint, as illustrated in this figure. The ESG scores are observable, but provide uncertain information about the firm's environmental performance. The same is true of reported carbon emissions, which are less subjective but become available with a delay and do not predict future environmental performance. Robust stochastic control methodologies may be used to build optimal portfolios in the presence of biases, errors, and uncertainty in the data. Quantitative finance models are based on financial data. Two types of data are used. Risk management methodologies are based on historical time series data to compute risk measures and identify stress scenarios. And parameters of pricing hedging models are calibrated to a snapshot of market data on any given day, such as listed option prices, to ensure absence of arbitrage. Given the scarcity of historical data, generative modeling is often used, from well-established Monte Carlo methodologies to more recent AI-based methods such as generative adversarial networks. Quality of data sources is analyzed as part of model validation and model risk management procedures. In sustainable finance, there is much more data which is often of poorer quality. Unlike financial data, which typically corresponds to prices of actual transactions recorded without error, extra-financial data comes in a multitude of formats and can be acquired from different sources with varying degrees of reliability. For example, numeric and textual data on environmental, social, and other impacts reported by companies and compiled by data providers with some quality checks. Textual data from newspapers. Data observed by physical measurements, satellite images, climate, weather, and so on. Asset-level data compiled by NGOs, data providers, etc., based on a variety of sources. Scenarios and projections produced by various organisms, NGFS, IPCC, IEA, World Bank. Indices, ratings, and scores computed by data providers, such as ESG scores. Many of these data sources are known to contain biases, and standards governing them are barely starting to emerge. Robust data governance and validation approaches must be established, and quantitative methods can be of help. For example, machine learning approaches can be used to estimate company impacts from asset-level data or satellite images, to double-check data reported by corporations. Natural language processing can be used to analyze news articles and/or company reports to detect greenwashing. Deep neural networks can be used to detect patterns in the data and forecast future impacts of extreme events and tipping points. Given the multitude of data sources, the data quality issues, and the difficulty to access reliable data, especially for academic research, in the recent years, non-profit initiatives aiming to construct reliable and publicly available extra-financial databases have started to emerge. One could mention NZPDU for data on emissions and other company impacts, Climate Trace for asset-level emission data, and the Platypus project at Louis Bachelier Institute, which aims to create a platform for dissemination of various types of extra-financial data for academic research.